Okay, in this video, I'm going to be going through section 3.5, which is over local linear approximations and differentials for AP Calculus BC. So in this section, we're going to start getting into the idea of using a simplified function to model a more complex function. And this is something that's going to be sort of a long-term concept for us. So we're going to talk about linear approximations today, but this is actually going to lead us into something that we're going to do in the second semester, which are called Taylor series approximations. So when we do a local linear approximation, we're actually doing the most basic version of a Taylor series approximation. So that'll make more sense as we go through this, but I just wanted you to make aware of, I wanted to make you aware of the fact that even though this is a relatively simple topic, this is something that is going to carry through long term. So it's not something that you just kind of, learn it and move on. It's something that we're going to continue to build off of later on in the year. So when we talk about local linear approximations, I usually refer to these as tangent line approximations, because all we're really doing is taking the equation of a tangent line at a point and using that as a rough approximation for our function when we're close to that point. So you can see on this diagram down below kind of what we're doing here. So we have this function f of x, and you can see that there is a tangent line drawn close to f of x. And what we're doing is we're basically saying, okay, let's say we know what f of a is. We know that exact function value. What if we need to know the function value over here? Well, what we're going to do is say, okay, well, a plus dx, where dx is a small change in our x value, is some point that's very, very close to a. And we're going to say our tangent line, if we're very close to a, is going to be a good rough approximation for that function value. Now, on this diagram, it looks like these two things are really far apart. It looks like my tangent line value or y value there is very different from the function value. But this is also, think of this kind of as a zoomed in view of what's happening. So in reality, we're going to have our tangent line be very, very close to the function. And so the approximation we get, yes, it won't be the exact value of the function, but it'll be very, very close to what the actual value is. So what we're trying to do is make it to where a really complex function that's difficult to work with, we're trying to find a more simplified function that's very, very easy to work with that we can use as an approximation. Okay, so since we're doing a tangent line essentially to approximate the value of our function, there's two things we need to know whenever we write one of these linear approximations or tangent line approximations. So remember the equation of a tangent line, we just need to know a point and the slope. So that's how we find the equation of a tangent line. We need our point slope formula, and that's what we're going to do here. So I've got a worked out example for you that I just wanted you to see how this is kind of going to operate. We've got f of x is 15 minus x cubed, and it says find the linear approximation at the point 2, 7. So what we're going to do is find a linear function that we can use to approximate this cubic function when we're close to x is 2. Okay, so you can see the requirements are f of 2 and f prime of 2. That's our point and our slope. And I found the derivative here to be negative 3x squared. I found my derivative value to be negative 12. And in the end here, this is my tangent line. Y minus 7 is equal to negative 12 times x minus 2. So for our linear approximation or our linearization function, all we're going to do is solve for y, and this is our linearization function. Okay, so when we have this function, what it's going to allow us to do is approximate the function value close to the value where x is 2. So for example, let's say I wanted to find f of 2.1. Well, f of 2.1 cubed, I mean, if we had a calculator, obviously we could do that very easily. But if you wanted to do this by hand, 2.1 cubed, yes, you can do it. It'd be kind of a pain. But what we're going to do is approximate it using our linearization function. So we know that that would be 7 minus 12 times 2.1 minus 2. And now it's something that we can just approximate in our head. So f of 2.1 is about 7 minus 0.1 times 12, so that would be minus 1.2, and we get 5.8 as our approximation. If you were to actually evaluate 15 minus x cubed at 2.1, you would see that you get a value that's about 5.7. I think it's about 5.74. So it's very close. We do have some error there, but as a rough approximation, it's not too far off. So that's sort of the main idea for this. Now, like I said before, we are going to get into more complicated models for functions later where it's not just a linear function, and that's what a Taylor series will do. A Taylor series will be a method that we can use where we can then use like a quadratic function to model our function, or a cubic or a quartic function. We can get into higher degree models, and that will improve our accuracy as we move around a curve like we have for x cubed. Okay, so we're also discussing differentials in this section. And the big thing to remember is when you see a differential expression, it's representing a very, very small change in whatever the variable is. So when I see dy, that's a very small change in the y value. When I see dx, that's a very small change in the x direction. And when we're doing this with a linear function, you can just think of the dx and the dy as the change in x and the change in y. So when we're working off of typical differentials, the dy is going to be our approximated value, or the approximated change in the y value, versus the actual change in the y value. And this will make a little bit more sense as we kind of talk through this. Okay, so this is our setup that we always use for the linearization of a function. And this is sort of set up like a formula, but in all honesty, this is not something you need to try to remember, because if you know how to find the equation of a tangent line, you know how to do the linearization of a function. And that's all this is. It's the tangent line, and then we've rearranged it to get it in the form of a linearization of a function. So this is, you know, what I would call the formula that we're going to use, where we've got y is equal to f of a plus f prime of a times x minus a. All that is essentially our y minus y1 is equal to m times x minus x1. We move the y1 over to the right side, just like we saw on the previous page, and now we've got our, you know, formula. Now, notice over here with these differentials, dx, that's my change in the x value. So you can write it in a shorthand as a dx. And then also, since we're dealing with a linear function, the change in y is going to be the slope times the change in x. Okay, so remember, since we're dealing with a tangent line approximation, that would be our approximated change in the y value. All right, so let's go through some examples of how we would actually use this. Now, this is probably not the most practical use of this method, because this is something we could just plug into the calculator anyway, but it just gives you something to use that's easy to understand and easy to compare to the actual values that you would see on the calculator. So it says find the square root of 1.01 without a calculator. And what we're going to do here is we're going to use a tangent line approximation to do this. So I need to start with a function. In this case, we weren't given a function. So if you have to write your own function to do your linearization, you want to make sure that with your function, you're going to be able to get a function value that's exact, very close to the point that you're looking for. You're also going to want to make sure that you can get the exact value of the derivative. So what I'm going to use here, and you'll see why in just a second, I'm going to use the square root of 1 plus x. And the reason I'm going to use that is because I know if I plug 0 into that function, I get the square root of 1 or just 1. I have an exact y value. If I take the derivative of that function, I'm going to get 1 over 2 times the square root of 1 plus x. And if I evaluate that at 0, that's going to give me 1/2. So the two things that I needed to know the exact coordinates for a point. I needed to know the exact value of the slope. And now from that, I can do my tangent line approximation, or my linear approximation. So what I'm going to do here is I'm just going to write this out using the equation of the line. Y minus y1 would be y minus 1 is equal to my slope times x minus 0. Okay, so that x minus 0 is kind of an important form to use. And the reason I want to keep it in that form is because that's showing me where my point of tangency was. So we call that the center point of our model. Our model is centered at the point where x is equal to 0. So if we move away from x is equal to 0, this is going to tell us how far we moved away from that point. So my actual linearization function would be solving for y. So y is 1 plus 1/2 times x minus 0. And I'm going to continue to write that x minus 0 because I want to make it really clear that my center point is at x is equal to 0. So here's my linearization function. It would be 1 plus 1/2 times x minus 0. So you can write it as just y. Sometimes you'll see that L of x representing the linearization function, and I want to use that notation because your book has a tendency to use that notation, but it's not necessarily required. So now the whole point of this question was to try to approximate the square root of 1.01. So what we're saying is the square root of 1.01 is going to be approximately 1 plus 1/2 times x minus 0. Well, go back over to our original form for our function. It was the square root of 1 plus x. If I want to make that into the square root of 1.01, I'm going to need to add 0.01 to that, or 1 over 100. So that would make this 1 over 100 minus 0. So in the end, I have 1 plus 1 over 200, which is about 1.005. And if you plug square root of 1.01 into your calculator, you'll see that that's actually very, very close to the actual value of square root of 1.01. 1.005 is very, very close. And the reason it's so close is that we didn't go very far from our center point to start with. And then the second thing is, if you look at the square root function close to where x is 1, it has a shape that's not too far from being linear. It definitely has a little curve to the graph, but it's not curving very quickly. So my tangent line is not deviating away from the function very quickly. So that allows me to get a really accurate representation of what the square root of 1.01 is just using that linear approximation. Okay, so I've got 2 more problems here that I want you to try. And what I want you to do is just pause the video and try to come up with the solutions for both of these using a method like I did up above, using a linear approximation. So go ahead and pause the video, and when you come back, I'll show you the solutions. Okay, and here are the answers that you should have come up with. For the first one, about 20.125. And notice that I did this one a little differently. I did it a little differently on purpose just so you could see that it doesn't really make a difference how I set this up, as long as I can evaluate my function and the derivative and get an exact value at a point that's pretty close to the point I'm trying to evaluate. So for this one, it was the square root of 405. So I said my function this time is just going to be square root of x. And a point close to square root of 405 that I know the exact value for would be square root of 400. So you can see that I went through here and I found f of 400 is 20. I also found my derivative at 400 is 1 over 40. So now I've got my derivative and I also have my function value. So here's my linearization once I've simplified it down. And then in the end, essentially what I'm doing there, the x minus 400 is the change in the x values, and I got a change in the x of 5. Okay, so from there, simplify it down, it's about 20.125. And again on that one, you'll see that you're very, very close to the actual value if you check the square root of 405 on the calculator. Now, if you notice on the last one, we didn't go very far from the center point. Our center point was at 0 for that one. We went 0.01 units away, and we got an error that was very small. Well, this one, we went 5 units away from the center point because the center point was 400. And I went 5 units away, and I actually got an error that's pretty comparable to the previous problem. And the reason for that is because, again, think about the graph of the square root function. When I'm way out here where x is 400, that graph is very close to linear. So since that graph is so close to linear out there at 400, I can go pretty far from my center point, and I'm still going to get a very accurate representation of the value that I'm estimating, you know, close to that center point of 400. So I could go out to 410, 420, 430, and I would still have a pretty accurate representation of what that value is using this linearization function. So it's all dependent on the shape of your graph in terms of how far can you go from that center point. We don't really get into calculating what's an appropriate distance to go from the center point. That's something that you would get into if you get it really heavily into studying differential equations in college. You can get into the idea of, okay, with this type of function, how far can I go from the center point? For us, we're not really going to get into that. I just want you to realize that depending on the shape of the graph, that's going to determine how far from the center point you can go. All right, so then for the last one here, it was cosine 1.75, and we're supposed to start at x is equal to pi over 2. So this one, they made it pretty clear what they want you to do. We're going to use the cosine function, and we're going to have a center point at pi over 2. So I didn't show all the steps this time, but I just wanted to show you the main idea. So my function is cosine x. My function at pi over 2 is 0. My slope at pi over 2 is -1. Then I can write the equation of my tangent line, and we get this value of pi over 2 minus 1.75. And you would see that that's pretty close to what the cosine of 1.75 is. And the reason is, if you look at the cosine graph at pi over 2, the cosine graph at pi over 2 is pretty close to linear. And we're not going that far away from that center point. So again, we're getting a pretty accurate solution, even though we went a pretty decent distance away from that center point. All right, so let's talk a little bit more about differentials. So I mentioned earlier that differentials, dx and dy, are just small changes in the x and small changes in the y. So dx is always going to be the actual change in the x. When I talk about dy is what my linear approximated difference in the y is. So if I do a tangent line approximation, that's how far the y value is changing. Delta y is how much my original function is actually changing. So delta y and dy are not exactly the same thing. And I'm going to go back to the diagram at the beginning here and just show you kind of what we're talking about. This one has delta f, and then I'm going to use a df here. But on this diagram, this distance where we're measuring the distance that we changed along the tangent line, that would be like my df. And then you can see the delta f is the distance that goes all the way from here to here. So the delta f and the df are a little bit different. The differential value, the df, is how far we changed the y value or the function value along the linear approximation. The delta value is what's the actual change in the function values if we use the function value we finished at minus the function value we started at. So they mean two slightly different things. df is really an approximation for delta f, is the way that you would want to think about that. Okay, so whenever we're talking about dy dx, remember that that's the linear change in y over change in x. Okay, the other thing to remember now that we've seen differentials is that dy and dx, those are just variables. So those are representations of small distances. So we can work with them just like we work with any other variable. We can add them, we can subtract them, we can multiply them, we can divide them. So just like any other variable, we've got the same operations that we can do. And what you will see here is a differential equation. It says solve for y. So we're looking at this example here. Solve for y. Well, what they're wanting you to do is just understand that if I have dy is 3x plus 7 to the 5th dx, this is a differential equation. The reason it's called a differential equation is because, just like the name of it, it's an equation that has differentials in it. But if I were to divide each side of this equation by dx, I would get dy dx is equal to 3x plus 7 to the 5th power. And then from there, we could find what y was using antiderivatives, or when we get into some of our integration techniques later on this semester and early next semester, we can figure out what the original function would have been. But the main thing I want you to get out of that is that you can actually get that in the form of dy dx by manipulating those differential expressions. Okay, so when you see an expression like the one that we had above, if dy is equal to f prime of x times dx, then y is equal to f of x. And it makes sense because essentially what we're saying here is dy dx is equal to f prime of x. Okay, so that's why we often use that f prime of x and dy dx as interchangeable, because they're essentially representing the same thing. You are going to see a few problems like these next two on your assignment, and they're very, very easy. I just want to make sure that you understand what they're asking you to do. It says find the equation for the differential dy. Well, here, if I took the derivative dy dx, I would get 21x squared. And all they're wanting you to understand here is that dy is equal to 21x squared times dx. So that's it. That's all they want you to do is solve for dy. They want you to understand that you can work with the dy and the dx just like you can with any other variables. All right, let's take a look at this next page. So this one just gets into, it's another same type of example. It just gets into what are we thinking about when we actually look at something like a dy. So here, my dy would be equal to negative 4 sine 4x times dx. And in terms of what does that mean? Well, if I'm looking at this as a linear approximation, my change in y is equal to negative 4 sine 4x times my change in x. So that's really all that's saying is how much is my y changing in relation to my change in x. All right, so let's take a look at a few examples with differentials. You're going to see some questions in your assignment that are going to deal with talking about error calculations, or they're going to talk about how much error do you have in using a differential to approximate the delta value. And I want to make it really clear kind of what they're talking about with that, with this example. So this example says the radius r of a circle increases from 10 to 10.1 meters. Use dA to estimate the increase in the circle's area A and compare this estimate with the true change delta A and find the approximation error. Okay, so we're dealing with the area of a circle. So we know area is pi r squared. And what they're wanting us to do is they want us to find the differential value of A, and they want us to find delta A. So the first thing is dA dr here would be equal to 2 pi r. And if I want to now find my dA, it would be 2 pi r times dr. Now remember, that's going to essentially represent, if this function were linear, how much is the area changing for a corresponding change in the radius. And essentially what we would use this for, like it shows over here, we can approximate the actual change in the area. The delta A is the actual change in the area by using this differential value. And so I'm going to use this differential value. I started with a radius of 10, so I'm going to put in 10 for the radius, and you can see up here, our radius changed by 0.1 meters. And what I get for a solution there is 2 pi meters squared. And so essentially what that is saying is, if I change my radius by 0.1 meters, I'm expecting my circle's area to change by approximately 2 pi meters squared. Okay, so that's my linear approximation for the change in the area. Now, the other thing they wanted us to do is look at what's delta A. This is the actual change in the area. So the area of the larger circle would be 10.1 squared, pi times 10.1 squared. So that's the area of the large outer circle in that diagram, minus pi times 10 squared. So this is my actual change in areas. It's about 2.01 pi meters squared. Okay, so you can see the actual change in the area and the approximated change in the area are not very far off. And if you think about it, our center point for this was at 10, and we went 0.1 units away from 10. And so we didn't go very far from our center point. So I would expect that I'm going to have a pretty accurate representation of the change in the area by approximating with a linear function as opposed to finding the actual difference. So the error in our calculation is just going to be the difference between the differential value and the delta value. And I do this as the absolute value because I just want to know what's the magnitude of my error. How far off am I? And it doesn't matter which direction I go here. So we can write this as a positive or a negative, but we typically report error as a positive value. Okay, so we are off by about 0.01 pi meters squared. Okay, so a little bit of vocabulary with that, the delta, the differential, and then when they talk about approximation error, that's what we're talking about with an approximation error. Okay, so I've got a couple more problems I want to go through with you here. Just really more than anything, it's more vocabulary. These are pretty simple for the most part. So this next one is what we call propagated error. It says the radius of a ball bearing is measured to be 0.7 inches. If the measurement is correct to within 1/100th of an inch, estimate the propagated area in the volume of the ball bearing. So essentially what we're looking at here is a tolerance. So when they manufacture things like ball bearings, each one of them is not completely identical. They're manufactured to be measured to within some certain tolerance. So let's say it has to be accurate to be within 0.01 inches, or they throw that one out because it's not accurate enough. So essentially what we're doing here is we're saying, okay, if we are accurate to within 0.01 inches, how far off could the volume be? And we're going to approximate how far off the volume is by using a differential. So that's where the estimate comes into play. So here's our volume function, 4/3 pi r cubed. If I took the derivative of that, you can see that it would just be 4 pi r squared. And my dv then would be 4 pi r squared times dr. Now notice the information that's up here. We've got the radius is 0.7. That's sort of like our center point. That's our perfect radius. We're going to be off by as much as 0.01 inches in either direction. And they want us to know, what is delta V? Well, what I'm going to do for delta V is I'm going to say delta V is going to be approximated by dV. So in this case, that would be 4 pi. My radius was 0.7. And my distance that the radius can change, or the amount the radius can change, is 0.01. So my delta V then is going to be approximately 0.0196 pi inches cubed. Okay, so not a really big tolerance. We're 1/100th of an inch is pretty small. So we're expecting that to be fairly accurate. And you can see that our estimated change in the volume is also very small. That the change that corresponds from the change in the radius is also very small. Okay, so that's propagation error. There's a lot of different types of error calculations that you're going to see if you read through the book. The only two that I'm ever going to ask you about are these two. When we talk about the approximation error and when we talk about the propagation error. So as long as you can understand what those are the ones that I want you to really focus on. All right, and then this last problem, I just wanted to show you the limitations that you run into when you do a linear approximation. And this really leads into why we get into Taylor series in the second semester and start looking at higher order models, meaning like a quadratic or a cubic or a quartic. So this function, it says, is e to the x sine 2x, and you can see it's plotted over here to the right. We know what f of 2 is, and we know what f prime at 2 is. They are asking us to use a linear approximation to estimate f at 2.3 and f at 2.9. So I'm not really going to go through and calculate this out. I just want to show you graphically what they're talking about here. So here's my point when x is 2, and my tangent line would look something like this. Okay, so if I'm at 2.3, which is, I don't know, maybe over here, you can see that the tangent line is still very, very close to the actual function value. So if I approximated f of 2.3, that would be a pretty good approximation. But think about where you are when you're at x is 2.9. So when I'm at x is 2.9, be about right here. I lost my tangent line there, but you can see the tangent line, since we're centered at 2, my tangent line is really, really inaccurate for that point. And the reason it's so inaccurate is because my function has completely changed directions since we went from 2 to 2.9. And so that whole idea of being relatively close to the center point and it being dependent on the shape of the function, this is what I'm really talking about. So when I was at 2.3, I'm still close enough that I'm getting a pretty accurate representation. But when I'm at 2.9, now it's pretty obvious this is really not a good model to approximate f of 2.9. So you can see how we're going around, sort of around a bend in our graph there. And that's where it would be really useful to be able to use a higher order model, like a quadratic or a cubic or a quartic type of function to model this. And then we'd be able to go much, much further from that center point of x is equal to 2. And we would be able to get a very accurate representation. So that's where we're heading with this in the second semester when we come back and talk about Taylor series. So for the homework, try to really focus on the idea that a linearization function is just a tangent line approximation. And then try to focus on what do those differentials actually mean. So when you do the homework, it's pretty simple, but try to really think conceptually about what you're doing so you're not just sort of blindly going through the algebra and the basic calculus steps. Try to really visualize in your mind what's happening graphically, and that'll help you get a better feel for what we're actually doing this for.